Good afternoon to everyone, and thank you for giving us a little bit of your time in this series of webinars where hopefully you're finding them to offer some nuggets, I'll say, of information that you can use. Today's topic is TVR evaporators. Thermal vapor recompression, or TVR, is what we use for short. It's a method to reduce the energy consumption of a steam heated evaporator. And I'll get into first in a review of what direct steam heated evaporators, how they work, and the functions, and breaking them into multiple effect evaporators, and then what happens when we implement a TVR. So, and the purpose of a TVR, thermal vapor recompression, is we use a high pressure steam source as the mode of fluid in an ejector, and to entrain a recycled low pressure steam source, typically water vapor that's been evaporated from a product, and then we discharge that combined steam and recycled low pressure vapor as a more useful intermediate, at an intermediate pressure, that we can use it as a condensing steam source. The vapor recompression cycle relies on condensation temperature of the lower pressure steam increasing as we go to the higher pressure. Now, when we go to evaporators, I've used this in previous presentations. You know, the heat transfer rate is equal to the heat transfer coefficient of the product, the available surface area, and the differential temperature. And those key points there, the U coefficient is product specific. And as I go into my examples later in this presentation, I'm going to be just using water. So water has a very good high heat transfer coefficient, and it's constant. Area, once we fabricate a piece of equipment, that area is also going to be fixed. And what that means is that we're primarily left with one variable, the temperature difference, in order to increase or decrease the heat transfer rate. Now, when we've got in my talk here, I'm going to focus on falling film evaporators, vertical shell and tube heat exchangers, where we've got the liquid flowing down the product liquid flowing down the inside of the heat exchanger tubes, and a saturating vapor or steam on the outside shell, condensing on the outside of those tubes. And in that, the shell side tube chest, as we often call it, operates at a higher absolute pressure than the tube side. And since it's at a higher pressure with saturated steam vapor, and inside the tubes, we are at a lower pressure, that creates the differential temperature to drive our heat transfer. Bear with me here. So I'll go with the first example of a direct steam heated evaporator, single effect. So I've got one effect here where I'm putting, in this case here, I'm going with 100 kilograms of steam going into the shell, and that's saturated steam. And I'm using the example here of 80 degrees Celsius, 176 Fahrenheit for the steam pressure coming in there. Now, in a direct steam heated evaporator, often we're coming straight off the boiler. We've got 100, 120 PSI steam, but we're going to let that down to whatever saturated temperature we need for heating in our evaporator. And in most of our cases, we're dealing with heat sensitive products, so we don't want to hit it too hard with temperature. Thus, in this case, the example I'm using is 80 degrees C as the heating temperature in the shell. So now that steam condenses, and at that temperature, if I condense 100 kilograms of steam, I liberate 55,150 kilocalories, or 219,000 BTUs of energy from that 100 kilograms of steam. And now that heat transfer from the condensation on the outside of the tubes transfers to the liquid on the inside, in this case water, and it's going to evaporate 98.9 kilograms of water. And that's because at the slightly lower temperature of 70 degrees, in this example I'm using, if you look at the steam tables, you don't exactly evaporate 100 kilograms of steam of water, but you're close. And I'm using this as the example to say that in general terms, we talk about 1 kilogram of steam evaporating 1 kilogram of water in a one effect direct steam heated evaporator. And I put the note here at the bottom that this example is all based upon the fact that the liquid product coming in the top of the calandria and falling down the tubes on the inside is already a boiling temperature. It's already been preheated. So all the energy goes to evaporation, none for preheating. Now, we can expand this now to a 2-effect or a 3-effect direct steam heated evaporator, where steam comes in the first effect, evaporates some water, and that water vapor at a slightly lower pressure now goes over into the shell of my second effect and evaporates some more water. And in rough numbers, we can say a 2-effect evaporator, we can evaporate 2 kilograms of water per kilogram of steam, or a steam efficiency of 2 to 1. 3-effect, similarly, a steam efficiency of 3 to 1, evaporating 3 kilograms of water with that 1 kilogram of steam coming in. Now, in the next slides, I'm going to get a little more specific on the numbers in a couple slides, forgive me. So just some vocabulary here on multiple effect evaporators. We commonly refer to number the effects in the vapor flow path. So the first effect is where the highest temperature heating vapors come in, and then it cascades down through the chain, second effect, third effect, following the vapor flow path. And of course, temperatures are decreasing as we go through this flow path, because if you remember, in that 1 effect direct steam heated, I was heating with 80 degrees C vapor steam, and I'm evaporating at 70 degrees. Well, now that becomes my heating temperature in the second effect. And the only way I can drive evaporation is if my second effect product side is at a lower pressure. In this case, 60 degrees C, and that goes further into the third effect, and I have to boil at 50 degrees C in that third effect. So you can see the temperature profile decreases down through the system. And you know, how far can we expand this concept in chaining together multiple effects? It's, for most product applications, it's limited by how low a vacuum can I effectively achieve in the last effect and still condense my waste heat vapors, and most commonly that's with a cooling tower. So if I've got a cooling tower operating at 80 degrees Fahrenheit, supply water 100, 105, discharge water from that condenser, effectively it's, you know, I might be able to get down to 110, 115 degrees Fahrenheit as my lowest boiling temperature for the back end and what we would call the last effect. Going to the front end of the first effect, how hot can I get? It's again going to be mostly effect of how hot can I get my product in that first effect before I start having burn-on issues or thermal degradation of the product. If I have no thermal issues, theoretically, if I've got 100 psi steam coming in that front end there, I can heat at 328 degrees F, and I could chain together a whole number of these calandria effects in series. In practical terms, the largest that we've done and worked on at Caloris is a 7-effect direct steam heated evaporator, using cooling tower water at the low end, 115 degrees Fahrenheit cold on the last effect, and we were boiling up around 210 degrees Fahrenheit up in the first effect. So now, evaporating water from water, and I'm giving you these numbers here, and I'm using these straight steps, 80 degrees, 70 degrees, 60 degrees, because I keep reusing these numbers as I go through the presentation. So in this particular case, the same case as heating in the 1-effect direct steam heated evaporator. 100 kilograms per hour of steam coming in, 80 degrees. I boil 98.9 kilograms an hour of water, liberated as vapor at 70 degrees. That becomes my heating source in effect 2. Evaporates 97.9 kilograms an hour at 60 degrees C. Goes to the third effect, 96.9 kilograms of water evaporated at 50 degrees C. So in this, you know, in real numbers here, I've got a steam economy of 2.9 to 1 in a 3-effect direct steam heated evaporator here, evaporating water. 100 kilograms an hour of steam coming in, combined 393.7 kilograms an hour of water evaporated in those 3 effects. And one last point here in the direct steam heated, and before I get into the TVRs, is that I've been talking about the vapor flow paths. That doesn't mean that the product has to go through that same path. And we build evaporators that go counterflow, where the product comes in the last effect and then goes sequentially up in counterflow to the vapors up to discharging from the first effect. In this particular drawing I'm showing you here, we're coming into the last effect for the first pass, then up to the first effect, and then discharging from the second effect. And why would we do that? Variety of reasons. In some cases where we've got a product where we want to get some degassing out of the product of non-condensable vapors, non-condensable gases before we pass it forward, we go through that last stage, and those non-condensable gases go straight to the condenser before we then proceed forward to the front end of the evaporator. And another example would be if we're evaporating, say, permeate. As we build concentration, the lactose can start to reach its crystallization point, and we can suppress that crystallization point by keeping it hotter. So then we build concentration at the higher temperature effects. So that is the summary of what I wanted to get into in the concepts of multiple effects and direct steam heated as the base point before we now get into TVRs. So thermal vapor recompression, and this is the using a steam ejector where a motive steam supply is used to create a suction, and you combine those streams and you discharge at a higher pressure than the original suction pressure. So it's based on an ejector venturi principle. And as I said there, you pass a mode of steam through an expanding nozzle. And it can be one steam nozzle, or a steam motive nozzle, or it can be multiple steam motives. This drawing I show here is it's an example of showing 3 steam nozzles in the middle of that, in the body. And steam ejectors are used for a variety of sources. We use them in evaporators as well for certain applications to pull vacuum. And if you stage steam ejectors in series, you can pull very deep vacuum, much deeper than you could with a liquid ring vacuum pump or some other device, and as low as 1 micron of mercury absolute. And this chart here, just to give you an illustration of that, suction pressure at 1,000, that's atmospheric pressure. So a 1-stage vacuum, TVR can pull down to getting close to 100 millibar of absolute pressure. You put that into a second stage there, you can step that up to, about down to 50. And you can sequentially go in, 4 stages in series, getting down to extremely low vacuum. So there's multiple uses for these steam ejectors that you'll see out there in industry. We use them for energy efficiency in our TVR evaporators. And just wanted to give you some quick pictures here. This is an example of a single nozzle TVR steam nozzle. And you can see the burn on here. This has been taken out for maintenance. And what you've seen there with the black is carryover from in the suction vapors coming in, carrying entrained product with it. It's burned onto that steam nozzle because, as you can imagine, that nozzle is pretty hot. And here is a picture of a multiple nozzle, in this case 4 steam nozzles that would be inserted into the throat of the steam ejector. So a little more detail here on the cutaway of how this steam ejector works. You have a motive steam fluid coming in and through the nozzle, and then you expand that steam flow, and the pressure drops. And you expand that through the suction nozzle, and you actually create a vacuum as it discharges from your nozzle, a vacuum that's actually lower than the suction, the absolute pressure of the vapor you're suctioning in. In this case, fluid 3, showing in the depiction here. And then as those streams combine, they expand, and pressure builds up again to a pressure higher than what the suction pressure was. And as you can see with the velocity chart here, you have extremely high velocity as that steam accelerates out of the nozzle and commingles and accelerates that suction fluid. And two phenomena that you can see with these Venturi thermocompressors is you actually have cold spots right around that mixing section on the outside. In certain conditions, if you don't have it insulated, you can actually see condensation and ice forming on the outside. And when you're staging multiple TVRs in series, you actually have to start worrying about ice forming inside the nozzle. Because when that pressure really drops at the mixing point, you can actually get below the absolute pressure where water wants to freeze inside the nozzle there, even though you're dealing with steam. And anybody who's worked with a TVR is going to be familiar with the whole concept of noise. And that's because of the acceleration here. When the steam accelerates out of its nozzle, it's supersonic, Mach 3 or Mach 4. And so they do scream. And so it's common that you're going to see a TVR it's going to look like a cylinder because it's been insulated. And commonly what we're using is sandpacking in order to get a good dense insulation layer around that to try and knock down the noise. So here we have two pictures of TVRs. On the left is the TVR is in a vertical orientation, and on the right it's in a horizontal orientation. We use both. It really depends on the physical layout of the plant, how many effects, how we're trying to squeeze it into the space available. No real functional impact whether it's vertical or horizontal. So now we'll get into the TVR evaporators here. And I've got a simplified model here, again, of a one effect TVR evaporator where I can evaporate 2 kilograms of water with 1 kilogram of steam supply. So I've got 2 kilograms of heating vapor coming into the shell of my calandria, evaporating 2 kilograms of water. And then 1 kilogram of that evaporated vapor gets sucked into the TVR as the suction vapor. A kilogram of motive steam, those commingle. I now have my 2 kilograms of heating vapor, heating steam. And I'm rejecting 1 kilogram of water vapor to the condenser. If you remember in the direct steam heated, it's a 1-to-1. For every kilogram of steam going in the system, I've got a kilogram of waste heat going to the condenser. And in the terminology I'll be using is steam efficiency of 2-to-1. And a pickup ratio of 1-to-1. That's the suction vapor divided by the steam flow. And it's common that we are typically dealing in pickup ratios of 0.5 to 1.2. And you'll see later it's in the presentation here as to where that may become a concern in some cases. And I just wanted to make a note here on density control. And typically that's what we're trying to do on these evaporators is concentrate a product to a final discharge concentration. So how do you control that? Well, when a direct steam heated, you put steam into the shell until you measure the discharge concentration and you back off on the steam coming in. If you're over concentrating, and then you increase the steam if you need to increase the concentration. And you control direct to the steam control valve going into the shell. In the case here, you're still controlling the steam control valve, except it's the mode of steam supply to the TVR, which is pulling off suction vapor and commingling those, creating your heating vapors going into the shell. What's critical in a TVR evaporator is it doesn't work well in in this cascading control if the steam pressure from the boiler fluctuates at all. A direct steam heated evaporator can tolerate fluctuating steam pressures. TVRs do not tolerate it well at all. So now getting into the more specific numbers on a one effect TVR heated evaporator here. And I went with the same numbers that I used for the one effect direct steam heated. 80 degrees C heating, 70 degrees C boiling, and the same 100 kilograms an hour of heating vapor going in, 98.9 kilograms of evaporation. Now, under this case here, I'm compressing suction vapors from 70 degrees up to 80 degrees. Not a lot of work to do for this TVR. So I can have a very efficient TVR performance here. It only takes 37.5 kilograms of 100 PSI steam into my TVR to create 100 kilograms an hour of heating vapor at 80 degrees C. Pickup ratio is 1.67, very good pickup ratio. Steam efficiency at 2.6, getting close to the steam efficiency of a 3-effect direct steam heated evaporator. And my waste heat rejection to the surface condenser is only a third of what it would have been if it was a direct steam heated 1-effect evaporator. So very efficient under this scenario. However, you know, evaporators, you run them for a full day, they start to foul. And what is your control mechanism to maintain evaporation as your product side starts to foul throughout a run? You have to increase your heating temperature. You have to increase that delta T. That's the only variable that's available to us here. So in this case here, now I've had to increase my heating temperature to 90 degrees C. Now I've got 20 degrees C compression required from the 70 degrees C evaporated vapors to the 90 degrees C that I need to compress to. That thermocompressor now is less efficient, still reasonably efficient as a 2-effect direct steam heated evaporator. But you know, that pickup ratio drops from the really nice 1.67 I had before to 0.85. So I'm actually now using more steam than I'm using suction vapor going into that TVR. And the steam efficiency dropped from 2.6 to 1.85. It's still pretty good. And of course, there's more waste heat rejecting to the condenser. And the key point for us designing evaporators is we have to design for fouled conditions, which means our surface condenser's got to be big enough to handle the fouled case of waste heat rejection, not the ideal case of starting from a clean evaporator. Now, 2-effect. You know, so that's a 1-effect. Let's see what we can do with a 2-effect TVR evaporator. So again, I went with the same 80 degrees C heating temperature, 70 degrees C evaporation in the suction, in the vapor on the effect 1, 60 degrees effect 2. Same numbers I used in the direct steam heated scenario. I've got a pickup ratio of 0.92 as I'm pulling vapor off of what's evaporated off the second effect at 60 degrees, compressing it to 80 degrees. 52 kilos of steam, 48 kilos of suction vapor. It's a very nice range for a TVR to be operating in. And steam efficiency here now is 3.8 to 1. I'm getting close to the steam efficiency of a 4-effect direct steam heated evaporator. And you know what that means is I can almost use half the steam than I would versus a direct steam heated 2-effect evaporator just by putting this TVR in. Now it's when I'm designing an evaporator, it's the capital cost. Do I go with a direct steam heated 4-effect and have the additional capital cost of effects 3 and 4? Or do I have the relatively nominal cost of a TVR and limit myself to the 2-effect evaporator and a lower capital cost? These are the cost benefit decisions we start making about whether to go with a direct steam heated versus a TVR evaporator. Now the same scenario here, I'm starting to foul out, and so I've got to increase my heating temperature into the first effect up to 90 degrees. So now my compression ratio is gone I'm compressing from 60 degrees C suction vapors evaporated off effect 2, heating it up to 90 degrees to go back into effect 1. So my steam is increased by about 20%. Pickup ratios dropped from 0.92 to 0.61. And my steam efficiency is down to 3.1 to 1. Still not bad. It's a little better than a 3-effect direct steam heated evaporator. And this is my fouled case. So it's still, from an evaporator standpoint, probably makes economic sense. So now I go to a 3 effect. Okay, so I've got, I'm pulling vapors now from 50 degrees C, because I'm taking the vapors off of the 3rd effect, vapor separator. And now, my pickup ratio, and this is on a clean evaporator, is only 0.6 to start with. I've got a really nice steam efficiency of 4.66, close to a 5 effect direct steam heated evaporator. However, as this evaporator starts to foul and I have to start increasing my heating temperature on effect 1, and I went to the case, what if I go to 90 degrees C for my first effect heating, 40 degrees C compression duty for this TVR. My steam goes up to 71 kilos an hour of the total of 100. My pickup ratio is only 0.41. And very likely what I'm getting into here is an unstable condition here where this evaporator is going to almost start thinking it's a direct steam heated evaporator. I can start to surge that suction vapor coming off the 3rd effect. And sometimes it'll suck vapor into the TVR and other times it won't. And it just gets into an unstable condition. And I end up dumping a lot of heat to that surface condenser, and it almost starts acting like a 3 effect direct steam heated evaporator. So looking at a design point, it's a little unfavorable to consider that TVR across 3 effects with that temperature profile. And there are a lot of variables here I'm not going into this simplified overview. So the solution to get comparable energy efficiency would be to compress just across the 2 effects. So in this scenario here, I'm taking evaporated vapors off of effect 2, and I'm compressing those up to effect 1 heating temperature. And basically half of what gets evaporated from effect 2 becomes my heating vapor in effect 3. And effect 3 is only doing half of what effects 1 and 2 does. But my TVR is now into a more comfortable operating range. In the clean evaporator, I've got a pickup ratio of 0.92. It's better than the 3 effect. I've got a steam efficiency of 4.73, which is better than the 3 effect was in a clean scenario. And as it fouls, and my heating temperature in the first effect has to go up to 90 degrees C, my pickup ratio only drops to 0.61. It's in a more stable range there. So this is why you will see, if you look in the industry, where we've got TVRs where we're picking up halfway through. And there are a number of evaporators out there in the dairy industry, for example, that are 6 effect, where there's a compression across 3. So you take evaporated vapors from the 3rd effect to create the heating vapors for the 1st effect, and then effects 4, 5, and 6 are just cascading what was left and what didn't get sucked into the TVR for the final evaporation stages. And a lot of that has to do because we've got less than 10 degree delta T across each effect, so the work on that TVR is not as aggressive. Anyway, I know I've been rambling here a bit, just trying to give you some concepts here as to, why is a TVR more energy efficient than a direct steam heated evaporator, and what are some of the limitations? And so I'll just go to my summary slide here, the pros and cons of a TVR evaporator. And the obvious pros are higher steam efficiency than the direct steam heated. I think that's pretty obvious from the scenarios I looked at there, and it's very easy to prove. And lower waste heat loading to the surface condenser and your cooling tower. And that's rejected waste heat that you're not using. And that's done because we're capturing part of those evaporated vapors and compressing them with steam to create our heating vapors. And in general, steam ejectors are very robust mechanical devices. There's no moving parts. And it's not uncommon for one of our customers to go several years without pulling one apart to inspect it. Not that we recommend that. You should probably do it every year, but it's been known to happen. Now, steam ejectors, we also use them in preheating, for product preheaters, as well as for pulling vacuum on, say, flash coolers. So there's multiple uses for these TVRs. And if you look at one of our large spreadsheets, you may see 4 or 5 of them shown on the drawing. Some of them we're using for preheating to just boost a little bit of available vapor to create our heating vapor for the preheater shells and pulling vacuum on flash coolers. And in one particular product case where there is some non-volatile gases coming off the system, we've actually found it's more energy efficient and cheaper capital cost to use a steam ejector to create the vacuum on the system altogether rather than using a liquid ring vacuum pump. Cons. And the cons on on TVR evaporators, of course, for a lot of people, it's the noise. They do create sound, and you can't really get around that. We can use sound insulation on the TVRs, but they're still loud. And they are very sensitive to fluctuations in pressure of the motive steam. And I was working once at a plant where we were trying to get the evaporator stable, and about every 20 minutes we'd lose evaporation, and come to find out it was every 20 minutes steam was being pulled for cleaning of a tanker or a silo somewhere in the plant, and the steam pressure at the evaporator TVR would suddenly drop 20 psi. And it just threw off the whole evaporator because we lost that motive steam pressure. TVRs really need a constant steam pressure supply in order to perform to their design. And on that point, they must also be properly designed for the vapor flows that are required by the evaporator, and then they have to operate there. There's a limited turn down range on a TVR evaporator. If you start backing off on the steam pressure too much, again, it suddenly loses the suction flow and starts to behave like a direct steam heated evaporator. And I said they are robust, but they are subject to wear. And periodically, steam nozzles, you've got water droplets of saturated stream going through those nozzles. They will over time get etched away, and they do periodically need to be replaced. Not every year, maybe every decade, but it all depends on the quality of your steam. TVRs are often inevitably located in a very difficult place to get to for maintenance. And because once they're up there, usually you don't have to do a lot of work to get to them. So and we're usually squeezing them in somewhere. And then the last point here is commingling of steam boiler condensate and the vapor that we've evaporated, the vapor condensate coming off the evaporator. And this has been a decision point in some applications to go to a direct steam heated evaporator because the customer wanted the steam condensate coming off the first effect to be able to go straight back to the boiler without any contamination of what might have been coming off the product. And they had a separate vapor condensate discharge stream. So the long and the short here is there are a lot of variables that go into selecting whether it's a direct steam heated evaporator or a TVR evaporator. And that's all weighed against an MBR evaporator, which we've talked about in previous presentations. And that gets pretty much to the end of my coverage here. I certainly hope I haven't rambled too much. I hope I got the key points across, and thank you all for your time.
Thanks, Bruce. I'm going to give folks a chance to type in any questions they might have. And in the meantime, you see on your screen there, we are having another webinar in 2 weeks on August 13th. Jim Kent will do a session on spray dryer safety, a very important topic. I don't know if you guys follow any publications like Powder and Bulk Processing, but there's every day a dryer fire happening somewhere in the country, it seems like, and most of them can be prevented if you're taking the proper precautions with your equipment. And so he will get into the tactics you can use to prevent fires and other calamities like that with your spray dryer. So if you are interested in keeping tabs on our future webinars or registering for the one you see on your screen, you can visit that link, caloris.com/caloris.com. webinars. And if you want to be among the first to know about upcoming sessions like today's, then I encourage you to join our mailing list if you haven't already. We send just one email per week. It's an industry newsletter with headlines from the news that are pertinent to processors, announcements like our webinar series, and other resources. And you can do that by visiting our website, scrolling down to the bottom of any page, and entering your email address where prompted. I haven't seen any questions come in yet. So Bruce, you must have done a very thorough job in describing TVR evaporators. But if you're feeling a little shy and you have questions you didn't want to ask in the webinar setting, you can feel free to send email to info@caloris.com. That goes directly to me, and then I can forward on your question to Bruce or whomever would be the best to answer your question. And we also are taking suggestions for future webinar topics. So with that, not seeing any questions come in, I want to thank everybody for joining us and thank Bruce for his presentation. And we hope to see you again in a couple weeks.